Hello! What I want to talk to you about today is how molecular orbital theory can give us some insight into the continuum of different types of chemical bonds, from covalent to polar covalent to fully ionic bonding. To do that, I'm going to be using this animation developed by Flick Coleman at Wellesley College. Now, you're familiar with this continuum already, based simply on the idea of electronegativity, that different atoms draw different amounts of electron density to themselves. But molecular orbital theory actually shows us the physical basis for why that's happening. What we've got here is a simple MO diagram for a diatomic system where the two atoms are the same. They have the same electronegativity, and because of that, the two orbitals have exactly the same energy. And what you can see is, because of the equal energy of the two atomic orbitals, atom A and atom B, they're contributing an equal amount to the bonding orbital that goes down and an equal amount to the antibonding orbital that goes up. And you can see that because the shape of the orbital is symmetric. You've got a bonding orbital that's the same electron density on both sides. You've got an antibonding orbital that's the same electron density and the same contribution from both atoms. What that means is, in this simple homoatomic system where the electronegativities are the same, so the electronegativity difference is zero, and you can see that in the diagram again because the energies of those two atomic orbitals are identical, you wind up with equal contributions to both bonding and antibonding because the energies of the two atomic orbitals are the same as each other. As a result, electrons that are in that bonding orbital, they're shared equally across the two atoms because the bonding orbital is symmetric across the two atoms, and this results in a covalent bond. Equal sharing of electron density on the two atomic centers, perfectly covalent bonding because the electronegativity difference is going to be the same. The electronegativity difference will be zero. But suppose I change that electronegativity difference. What will happen is I will also change the energies of the atomic orbitals, and they won't be the same anymore. As I make one of these atoms more electropositive and raise the energy of its atomic orbital, the relative contribution of the two atoms to the low energy bonding and the high energy antibonding changes. What happens is the more electronegative partner has the lower energy orbital, and it winds up contributing more to the bonding. So the bonding orbital looks more like the electronegative atom. The more electropositive atom gets a higher energy orbital. It winds up contributing more to the antibonding orbital, to the higher energy molecular orbital that results. And as I increase that electronegativity difference and increase the energy difference, you can see that the amount that the orbital skews to one side or the other also increases. Now we're looking at a heteroatomic bond with slightly unequal electronegativities, so the delta chi is not zero, it's more than that. And what happens is we get unequal contribution to both orbitals. The more electronegative partner with the low energy orbital contributes more to bonding. The more electropositive partner with the high energy orbital contributes more to the antibonding. And as a result, the two orbitals don't look the same. The bonding orbital skews to one side. It looks more like the electronegative atom. It has higher concentration on that atom. The antibonding orbital skews the other way. It has greater concentration on the electropositive atom. It looks more like the atomic orbital from that more electropositive center. But the electrons in the bonding orbital now wind up moving over because the electron density in that orbital shifts, and the electron density in the bonding orbital is more localized on the more electronegative atom. That's why the electronegativity manifests as it does. The lower energy orbital draws the electron density toward that side, and we formed a polar covalent bond because the electrons aren't shared equally anymore. They are more highly concentrated on the electronegative atom side that's contributing more to that bonding orbital. But suppose I keep going. I can increase this electronegativity difference so that the electronegativities are nothing alike. There's a difference of 2, even 3 between these two atoms. And now what you wind up with is effectively no shared overlap of those orbitals at all. And now you can see that the low energy orbital is essentially just the atomic orbital from the electronegative low energy partner. The high energy orbital is essentially just the atomic orbital from the high energy partner, the electropositive partner. And so now we have a very, very skewed heteroatomic interaction, essentially no interaction at all. Completely separate contributions to the high energy and the low energy orbitals. You can't even really call them bonding and antibonding. There's no overlap. And so the two orbitals that result simply are the atomic orbitals you started with no change, exclusive contribution from the low energy and the high energy, from the high electronegativity and the low electronegativity partner to make these two orbitals. Now the electrons aren't shared at all. They're localized. And if there are electrons in that low energy orbital, they've been completely transferred to the more electronegative partner. Effectively, you have an ionic bond. What this analysis shows you, though, is that these are not three distinct categories of bonding. They are just on a continuum, a sliding scale back and forth. As the electronegativity dials up or dials back, then the electronegativity difference manifests as a slight skew and a slight difference in the concentration of the orbitals to one side or the other side, and the bonding density changes as a result. It's best not to think of these as three separate categories, but just as points on this sliding continuum where the orbitals change gradually from one partner to the other, bonding and anti-bonding, more and less electronegative, as the energy difference skews. But it's a very, very simple model to carry in your head because intuitively it does make sense that the electrons will wind up concentrating on the electronegative partner. Now you can see that that's because the electronegative partner always concentrates and delivers more of its orbital density to the bonding orbital. That's where the electrons wind up. Go ahead and review any parts of this video that didn't make sense to you the first time. We'll be dealing with this later in class, and it'll be a concept that we develop further as we move through the course. But I hope you enjoyed this video. Thank you for watching.